Hello everyone, in this robotics and mechanical engineering tutorial we explain how to correctly calculate the mass moment of inertia by hand. The skills that you will learn in this tutorial are very important for robotics, mechatronics and mechanical engineers. So let's start immediately. Here's the problem. Consider a solid cylinder with a radius of r, uniform density ρ and height h. Our task is to compute the mass moment of inertia about the z-axis. To be able to solve this problem, it's first very important to properly understand the definition of the mass moment of inertia. To define the mass moment of inertia, we need to consider a small piece or an element of our cylinder. Over here, I will illustrate this element. It's a cube, and here it is. Next, we assume that the mass of this cube is denoted by dm. In this notation, dm, m denotes the mass, and d denotes an infinitesimally small mass. Next, we assume that this small piece, or this mass dm, is at the distance of r from the axis z. And here, we denote this distance by this vector r. Here it is. The vector r starts from this axis z and ends at this piece. And this vector makes an angle of 90 degrees with respect to the axis z. Next, let's denote the intensity of this vector by r. That is, r is simply equal to the intensity of the vector. Then, the mass moment of inertia of this whole body, that is of this cylinder, is defined like this. First of all, we need to define the mass moment of inertia of this small piece. It's denoted by d I with an index z. Let us denote the cylinder and its volume simply by c. Then, let the intensity of the vector r simply be denoted by r. That is, r is equal to the intensity of the vector r. Next, let's define the mass moment of inertia of this infinitesimally small mass dm. It's defined like this. d I with the subscript z is equal to r squared multiplying dm. In this notation, I denotes the moment of inertia and z denotes the axis. Now we are ready to define the mass moment of inertia of our cylinder. It's defined like this. Iz, this is the notation for the mass moment of inertia about the axis z, is equal to an integral over the volume of this cylinder c, and we denote this integral like this, and inside we have r squared multiplying dm. Let us try to understand this definition. Loosely speaking, the moment of inertia of the complete cylinder is obtained by integrating the moments of inertia of the infinitesimally small masses. Or in other words, we are summing the moments of inertia of these small masses and we are summing them up together to compute the complete mass moment of inertia. That's it. This defining equation can also be written like this. Iz is equal to, instead of this single integral over the volume, we can write a triple integral over the volume c, and then we will similarly have r squared dm. Next, instead of dm, we can write density multiplying dv, where dv is the volume of this infinitesimal piece. If we now substitute this expression for dm in these two equations, we obtain this equation, that you will often find in books, Iz is equal to an integral over c rho multiplying r squared multiplying dv. Or we can write this equation in a triple integral form, c rho r squared dv. And that's it. Due to the circular geometry of this cylinder over here, it might be difficult to directly apply this equation to our case. However, there is a more elegant way for computing the mass moment of inertia of this cylinder, and let's explain it. Over here you can see a sketch of the main idea for computing the moment of inertia. The main idea is to split our original cylinder into a number of shells. That is, to segment the cylinder by using shells. Here is a single shell that's at the distance of r from our axis z, and here is the isolated shell with its dimensions. The height of the shell is obviously the height of the cylinder, that is, it's equal to h. The width of the shell is dr. And over here you can see the top of the cylinder and a single shell. Next, we can unfold this shell, and as the result we will obtain this cuboid over here. Let's analyze the dimensions of this cuboid. Its height is equal to h. This is because the height of our shell is equal to h. Its width is dr. This is because the width of our shell is dr, and the length is 2 multiplying pi multiplying r. This formula for the length is obtained by applying the formula for the circumference of a circle to the top circle of the shell. Namely, we know that the circumference of a circle is 2 multiplying pi multiplying r, and consequently we obtain the length of our cuboid. Next, let's derive the expression for the moment of inertia of our shell for the z-axis. The moment of inertia of the shell will be denoted by di. And di is equal to r squared multiplying dm. Notice over here that I'm using capital dm, since I used lowercase m for the cuboid over here at the beginning of this tutorial. Next, let's analyze what is dm. That is, what is the mass of our shell. The mass of the shell is simply equal to the density of the material multiplying dvm. Now, what is dvm? That is, what is the volume of our shell? Well, from this figure over here, we can see that dvm is simply equal to h multiplying 2 pi multiplying r multiplying dr, and that's it. If we substitute this expression for dvm in the expression for dm, we obtain that dm is equal to rho multiplying h multiplying 2 pi multiplying r dr. Next, let's substitute this expression in the expression for di, and as the result we obtain that di is equal to, let's see, it's equal to rho multiplying h multiplying 2 pi, and over here we will have r squared multiplying r, that's r to the power 3 multiplying dr, and that's it. By integrating this expression, we can obtain the final formula for the mass moment of inertia of our cylinder. That is, Iz is simply equal to an integral of di over the volume of our cylinder C. Now, this integration actually becomes an integration over r. Let's show that. If we substitute di by this expression, we will obtain this integral. It becomes the integral of rho multiplying h multiplying 2 pi r to the power 3 dr. And since the integration is performed over the complete volume, and the volume is segmented by a number of shells, we need to perform the integration from 0 to r. That is, for every fixed r, we obtain a shell. If we now sum all the shells from 0 to the complete radius of our cylinder, we will do this integration. That is, we will perform the integration over the complete volume. Let us compute this integral. Iz can be written like this. Rho, h, 2 pi are constants. Consequently, they can be written in front of the integral. So let's write them. Rho multiplying h multiplying 2 pi, and we are left with the integral from 0 to r to the power 3 dr. Next, let's evaluate this integral. This becomes rho multiplying h multiplying 2 pi, and integral r to the power 3 dr becomes r to the power 4 over 4. And let's not forget the bounds. The bounds are from 0 to r. Let's simplify this expression and let's evaluate the bounds. Our moment of inertia is equal to 2 and 4 can be cancelled, so we are left with rho multiplying h multiplying pi. Then we will have this thing divided by 2, since 2 and 4 can be cancelled, and if we substitute the bound, we will have r to the power 4. And this is the final expression. However, let's write this expression in terms of the mass of the cylinder. The mass of the cylinder can be written like this. It's equal to the density of the material of the cylinder multiplying the volume. The volume of a cylinder is simply the cross-section area of the base circle multiplying the height h. Consequently, we will have r squared pi multiplying h. So how to use this formula over here? Well, let's first of all create a mass over here. Iz becomes, we will here have r squared, and we will be left with r squared over here. Then this 2 can be written over here, right? And we are left with this term, rho multiplying h multiplying pi, and this multiplying r. And we can see that rho multiplying h multiplying pi multiplying r squared is actually the mass, and consequently the expression is r squared divided by 2 multiplying the mass of the cylinder. And that's it. And the final expression is the moment of inertia over a cylinder is the radius of a cylinder divided by 2 multiplying the mass of the cylinder. And you will often see this formula in the books. Okay, that's all for today, and thanks for watching.